Hello and welcome to the Rubidium Signal Purity with Phase Noise Performance video by Anritsu. In this video, we will be showing real phase noise performance of a representative MG36221A 9 kHz to 20 GHz rubidium signal generator. After the phase noise live demo, we will be discussing use cases and customer applications where this phase noise performance is most important. Here we have a live demonstration of a standard MG36221A connected to a dedicated phase noise analyzer. We find it helpful for users to see an actual setup and performance of an instrument beyond the usual specifications that are found in a technical data sheet. In this demonstration, we have two engineers performing a phase noise measurement. We can clearly see from the output of the phase noise analyzer a clean phase noise plot with a clear pedestal region. The rubidium signal generator is set to 10 GHz with a 10 dBm output signal. It is clear that rubidium delivers an unprecedented level of performance from the live demonstration that we just showed. But how does that compare in the arena of various signal generators on the market currently? To make this comparison, we will use an actual screen capture of rubidium's performance. I will now juxtapose on this plot what will be known as the industry standard until now for standard phase noise. This phase noise is roughly around -120 dBc per hertz. Another key point to mention is that at -125 dBc per hertz, typical specification, is the common and accepted value for the first tier of phase noise improvements through vendor phase noise options. For an accurate comparison, standard rubidium signal generators, meaning no phase noise options, have a typical phase noise of -132 dBc per hertz. Rubidium establishes new industry standards for phase noise, outperforming both standard and low phase noise performance of top signal generators. Over the course of the next few minutes, we will discuss some use cases and why phase noise is important and vital to system performance. Please note that this list of examples is not exhaustive. We will discuss the following use cases: LO source within radar system measurements, LO source within radio transceiver systems, and effective number of bits or ENOB for A to C measurements. We will begin with radar system measurements. The diagram below is a common setup for radar systems. While the user is free to select a suitable signal generator for the RF signal output, it is important to mention that users can also benefit from the phase noise performance of rubidium when used with a pulse modulated signal. Additionally, rubidium has options for pulse modulation, including a quad pulse generator that enables users to simulate a variety of radar return signals from 1 to 4 targets at varying distances, or moving target either approaching or leaving. An additional benefit is that users can receive this functionality within rubidium's pulse modulation option, whereas an additional pulse train option is required with other signal generators. Let's return back to the radar setup measurement. We will now dive into why phase noise is important in this application. If we look at a real-life example like the one below, we can see that a radar is sending a pulsed RF signal that sees a plane and returns that signal. As mentioned before, we are using an MG36221A as the local oscillator, or LO, in the up-down conversion stages. So why is it important to have really good phase noise in this application? Well, the answer can be seen in the below illustration of two different phase noise plots. The green plot shows a wider phase noise profile, while the gray plot shows a slimmer phase noise profile. You may also notice that some kilohertz down from the signal, there is a frequency shifted and attenuated signal, which is the reflected signal from the radar target. The frequency shift is a result of Doppler shifting, and the attenuation is also a natural phenomenon of free air attenuation. It should be noted that the return signal can be very low in signal strength and almost unnoticeable if phase noise parameters are not adequate. Had the user performed this measurement via the higher phase noise option, the signal would be entirely missed or masked by the phase noise skirt. With rubidium phase noise, this very low reflected signal from the target is detectable. The next use case is also an LO source, but for a different application which has different requirements. While the setup looks familiar as the radar measurement setup, phase noise plays a different role in this measurement. A pure LO source is essential to test IF up and down converters in transceiver chains. Phase noise is especially important and critical when higher order complex modulation formats are used to send information. Once again, users may want to ask, why is this important? Phase noise is important because signal fidelity is based on the total noise contributed by the LO source to the signal, which is directly proportional to the integrated phase noise across the signal bandwidth. From the illustration below, there is clearly less integrated phase noise within the integration bandwidth zones for the lower phase noise plot, which is gray. To make this point clear, we have a simple example of digital modulation where phase noise affects performance. In the left image is a simple QPSK, and on the right, 16 QAM. It should be clear that in QPSK, there is quite a bit of margin for the signal within the parameters. But for 16 QAM, we will already see errors with phase noise that is not adequate to create a distinct signal within the confined parameters. Please note that this is the simplest case and that digital modulation schemes are far more complex, with systems supporting 1024 QAM and higher. The final example that illustrates why phase noise is important in measurements will be the effective number of bits measurement. When we talk about ADC measurements, we care about signal-to-noise ratio, or SNR, spurious free dynamic range, and effective number of bits. What is truly important to understand for this example is that the effective number of bits, or ENOB, corresponds to a certain amount of SNR, and there is a relationship between SNR and ENOB. This can be easily quantified by the below equation. We will now display a table that shows the values for SNR with respect to effective number of bits of an ADC. It is important to also note that the signal generator used as the input RF signal should have very good phase noise and harmonic performance, as this will contribute to ENOB measurement accuracy. The signal generator used as a clock source must also have good phase noise, especially in the pedestal region above 10 kHz offset from the carrier. Phase noise of a signal generator is so important because it determines the SNR at the signal and clock inputs of the A to C and contributes to the ENOB measurement at the output of the A to C. Higher SNR from the signal generator enables a better ENOB measurement of A to Cs with higher resolution. We hope that you have found this information video useful for understanding why phase noise is critical for measurements. Thank you for joining us today, and for more information, please visit www.anritsu.com.